Hello, everyone. Welcome back to the class. I hope you have had a joyful extended spring break and you're keeping yourself healthy and ready to begin the rest of our semester. Today, we are going to review a little bit of what we discussed previously in chapter 3, and then we will extend our previous discussion on other topics. So, some of you might find part of this discussion a little bit boring because you already have had it, but I want you all to be please patient, pay attention to this one, and make sure that you go over this one, complete it, and then you will be ready to jump on the next topic. Today we will review a little bit of the property diagrams for phase change processes of pure substances. This is what we discussed in previous section. Then I'm going to introduce you a new thermodynamic property called enthalpy. We're going to use this property a lot when we're discussing about the energy analysis of closed systems. After that, we will go over thermodynamic property tables and we will see how we can find the relevant tables to solve the problems. And finally, we will practice how to find properties of substances in single phase regions, meaning that we will use, for instance, the superheated tables in this section. In next section, we will go over two-phase regions, and we will also try to find the properties of the liquids without having the tables for them. All right. So by the end of today, you will be able to draw property diagrams, and this is very important because to analyze thermodynamic cycles, especially, and also to do a good analysis on thermodynamic processes, you need to be able to draw a good schematic of that process with respect to the uh, usually with respect to the saturated dome. All right, this is very important. We will practice a little bit on this one, and you will learn by the end of today how to do that. You should be able also to define the concept of enthalpy as a thermodynamic property, right? It is a property just like temperature, pressure, internal energy, and so on and so forth. And that is the reason why we can tabulate it, right? You also, by the end of today, will be able to determine the phase of a substance using the given data in the problem, right? In the problem, usually you are given, for instance, the temperature and let's say pressure. By having only these two properties, uh, you should be able to determine if your material is in subcooled region or is it superheated or maybe a mixture of both, right? That's what you will learn today. And finally, if we find out that a material is in single phase, then by the end of today, you will be able to determine thermodynamic properties of that pure substance. All right, using thermodynamic tables. All right, let's a little bit review what we learned previously. Previously, we discussed about the phase change process, and we began our discussion on a very, very simple process, an isobaric process. And with a simple experiment that you can do in the house, we drew the TV diagram for water. How did we do that? We just simply conducted uh, heating water in a piston cylinder under constant pressure, right? And then by that, we found the isobaric process lines, which are the dashed lines showed here. Okay, if we repeat the experiment for several pressures, right, then we will be able to have lots of these lines. Then by connecting the breakpoints of the lines, we will be able to find the saturation dome. And this saturation dome, which is a very important graph for thermodynamics, whatever we have in the left hand side of the diagram is compressed liquid, or what we call subcooled liquid, meaning that if, for instance, the temperature of water, right, is given to you to be 20 degrees Celsius, all right, let's say somewhere here, somewhere, oh, my apologies, somewhere like this. Let me see how I can write with this. Here we go. Okay, here is my pen. Let's say the temperature is somewhere here, and then the specific volume is 0.001 cubic meter per uh, per kilogram. Then we will reach to somewhere like this. This is my temperature, and this is my specific volume, and my property will be my state will be something like this. In that case, if it happens, then my thermodynamic state is at the left hand side of this graph, then it means that my substance is actually in liquid phase, right? So this is my compressed liquid region. If it happens that the state of the material is under the dome, anywhere under the dome, then I have a mixture, right, of saturated liquid and saturated vapor, meaning that my part of my material is in liquid phase and the rest of it is in vapor phase. Right? Like the condition when the water is just boiling and vaporizing. But if it happens that my temperature is so high or pressure is so low, and then I happen to be in the right hand side of this graph, it means that the entire material is in vapor phase, right? So, and three more important things. One thing, and they are about not the region, but about the line. Look at the apex of this graph. The apex of this graph is the critical point, all right? The critical point is unique for any pure material. And we have only one critical temperature, one critical pressure, one critical specific volume, right? And beyond that point, what happens is that our material, when we're changing its phase, for instance, by heating up the liquid, is not gonna go through a phase change with two-phase mixture. Instead, it will continuously change the phase. Something like this. Assume that for this case, the pressure is above the critical pressure of the water, and I am heating up the water. If I begin from some point like point one here, and I heat up at very, very high pressures, then it is gonna go such a path. And in this path, I can never ever visually find out two distinguishable phases, right? Which means that my properties are changing continuously, right? This is what we call superheated region. All right, later we will discuss much more about the superheated region and its importance in thermodynamic, especially in power cycles. All right, but but uh, below that critical point, this is supercritical region is for about that critical point, about the apex of this saturation dome. But below this point, in the left-hand side, I have a line. This line is the saturated liquid line. This is all the cases when I have 100% liquid, but that liquid is about to vaporize. Right? We call it saturated liquid. On the right-hand side, I have saturated vapor line, which is actually all the states when my material is 100% vapor, but it is about to condense, meaning that if I remove just a little bit of the heat from it, it will begin to condense, right? So, with that said, let's go over our next graph. We said that we can repeat similar experiments, right, to find other graphs. For instance, a graph for the pressure versus specific volume. In this case, what we're doing is we are actually conducting experiments for constant temperature, or what we call isothermal processes. And the results are these dashed lines. Okay, if I increase the temperature, I will have similar dashed line, but in higher, right, in above the previous line. If I repeat this experiment for various temperatures, right, and I keep all of them constant temperatures, I will have lots of these dashed lines. Then I can go and connect the breakpoints of the dashed lines, which allows me to find the saturated liquid line and saturated vapor line. And these two lines, we know that reach to each other at the apex, which is our critical point. Pretty much similar to the previous graph that we had. In this graph also, the left-hand side of the graph is all the states when our material is compressed liquid or subcooled liquid. Below this dome are the mixture of saturated liquid and saturated vapor. In the right-hand side, we have superheated vapor. Again, if we focus on the lines rather than the regions, the left part of the line is saturated liquid line, and the right hand side is saturated vapor line, right? Okay, with that said, let's see what can we do with these separate graphs if we want to combine them and make one single diagram for the properties of pure substance. We can actually do that, and by doing that, we can generate a surface. This surface is the pressure specific volume temperature surface. This is a unique surface for any pure substance, and it shows us all possible states for a material. All right, for instance, this one is for water. If we look at the projections of this space, the projections of this space, this surface, is actually what we found previously. For instance, look at this uh, front view of the graph. If I just focus on the front view of this graph, let me just show it in a little bit better form. Here we go. This is my front view. If I look at the front view, I will see only the pressure and the specific volume, right? And from the region's point of view, what I'm gonna see is these shadowed regions, okay? So I will have the PV diagram where this shadowed curve is my two-phase region. As you see, the top of this two-phase region here, this point, right? This is my critical point, all right? Above that point, these are supercritical regions. This is supercritical region, right? Let me write down, this is supercritical condition. These are supercritical. These are above the critical point. Okay, this is my two-phase region. This is liquid vapor region. On the right-hand side of it, I have the liquid. On the on the right-hand side, I have vapor. The left-hand side, I have liquid. Now, one important thing is this line at the bottom of the shadowed region. This line is a line on which I have all three phases of material simultaneously, and we call it triple line. This is when the liquid, the vapor, and the solid, all of them are in equilibrium, right? Okay, this is a very important line, and we will return to it when we're discussing about power cycles, right? I will return to this line because this line actually defines the minimum temperature that we can reach in a power cycle. Why? Because obviously below this line we will have the solid phase, and that is something that we don't like in our cycles. We don't like the water to freeze in the pipes. So this is an important limit for us. For the entire semester, our discussion will be limited to the regions above this triple line, and usually, not always, but usually below the critical point. All right, usually, not always, but definitely always we're gonna be remain above the triple line because we don't like the solids in our systems. All right, one important graph that we can draw using this surface is the PT diagram, or pressure temperature diagram. To draw the pressure temperature diagram, we need to focus on the side projection of this graph, right? If you look at the side of this diagram from this region, my apologies. Okay, here we go. If you look at it from this region, from this from the side, then you will see temperature and pressure. Okay, this is the graph of temperature and pressure. Look here in this graph. This is pressure temperature. In this graph, one thing is important for me, and that thing is that the triple line, if you look at it from this view, right, on the temperature pressure diagram, the triple line will be reduced to a point. It will be triple point. That triple point is a specific temperature and pressure at which we have all three phases of the material, right, in equilibrium. And if you remember, when defining the temperature scales, we said that the base of the lower temperature of the Celsius system is this triple point, all right? The triple point of water is exactly 0.01 degree Celsius. All right? Okay. With that said, now let's go define the enthalpy, and later by defining the enthalpy, we will go and use the thermodynamic tables, right, to find the properties. Keep in mind that we draw these diagrams to help us understand the processes. Back in old good days, engineers used the diagrams to find the properties and model the thermodynamic processes. Now, nowadays, By the advent of computers and the softwares and so on and so forth, we need tabulated data. That's the reason why we are going to focus on the tables. But it doesn't mean that you cannot use the graphs to solve the problems. All right. Later, if we find the time, I will teach you how to use these graphs effectively as engineers, right? That is not our main method, but that's a good alternative for some of the applications of thermodynamics, like for instance, designing HVAC system. If you're designing a heating system or an air conditioning system, usually it is much better to use the graphs rather than the tables. But for the rest of the systems that we analyze in this semester, the using tables are easier. So we are gonna draw the graphs to have a good schematic of what happens, right? And then we will use tables to find the unknown thermodynamic properties. And that's what we're going to do today. But before going over the tables, I want to introduce one thermodynamic property that we haven't discussed about previously. And that thermodynamic property is enthalpy. Enthalpy is actually combined property, and it is important usually in the open systems. Okay, usually in the open systems, the energy transferred by the fluid into a control volume is the summation of the internal energy of the flow that is entering the system and the pressure work, which is PV, right? Summation of these two, U plus PV, is called enthalpy. Like the internal energy, the unit of the enthalpy is kilojoules. And enthalpy is actually a property for the total mass, right? But we can divide the total property by the mass and find specific enthalpy. And this specific enthalpy is actually an intensive property. And because it's an intensive property, we can tabulate it. Again, just like the uh, internal energy, which has the specific internal energy, which has the unit of kilojoules per kilogram, enthalpy or specific enthalpy has also the same unit of kilojoules per kilogram. So let me just write down here that H, right? H, lowercase h, equals actually the capital H divided by mass. Pretty much similar to U, right? You remember we said that a specific internal energy equals total internal energy divided by mass. All right. Uh, Later, we will learn much more about this enthalpy and we will learn what it is. But for now, just keep one thing in mind. The latent heat of vaporization of any pure substance equals the change in its enthalpy from the saturated fluid to saturated vapor, right? HFG. This is this is what you will find in the tables, and this is what you will use later for evaluating the energy, right? The heat used to vaporize a substance. All right. Yeah, we will go over it later, but just keep in mind that this H is actually the summation of U plus PV, and it is a thermodynamic property. All right. Now let's see how we can use thermodynamic uh, properties. Let me see. Okay, property, using properties. Let me see. Here we go. Uh, okay, let me see. What do I have here? Okay, here we go. First of all, what we want to do from now on, we want to use the thermodynamic property tables to find unknown properties of a pure substance by having just a few properties. All right. What we have to do, first of all, in order to find the properties of a material, you have to find what is the phase of that material. Let's say I tell you that find the properties, or find, for instance, the specific volume of water in the condition that the temperature of water is 300 degrees Celsius and its pressure is 12 atmosphere. All right. Before you can use the tables to find the properties of water in this condition, you should be able to tell me whether the water in this condition is a liquid, or is it vapor, or maybe a mixture, right? That's the very first step. So we will identify the region using the saturated tables of the substances. I will go over the details of this one later. But how we do that? If in a problem the temperature is given, right? Then we are going to use the tables that are tabulated based on temperature. Okay? We will use temperature, and then we will compare the second property. Keep in mind that we said previously that in order to define the state of a substance, of a pure substance, right, we need to have two intensive properties. That's that's a state postulate. So if I'm given temperature in a problem, it means that I have temperature and a second property. So I go use the temperature table, right? With the saturated, for instance, the saturated water table that is tabulated based on temperature. And then I look at the given temperature, and in that temperature, I compare the second property that I'm given with the properties of saturated liquid and saturated vapor at the given temperature. Now, the next step, after I compare it, it is going to be my second property is going to be either less than the properties of saturated liquid, or it will be between the saturated liquid and saturated vapor, or it's going to be more than saturated vapor. Right? Based on this, I can make decision what the status. Similarly, if I'm given pressure instead of temperature, and the second property, for instance, I'm given the pressure and internal energy, I use the pressure tables, right? Keep in mind that I'm using saturated tables, but I'm using the saturated water tables that are tabulated based on pressure. And then definitely I have another property as well, for instance, internal energy. I compare the internal energy at the given pressure with the internal energy of saturated liquid and saturated vapor. Again, I'm going to have either of these conditions, either the internal energy that I have is less than the internal energy of saturated liquid, which means that my material is subcooled liquid, or it is something in between the saturated liquid and saturated vapor condition, which means that I have a mixture. or it might be more than the internal energy of saturated vapor, which means that my condition is superheated. All right. So after defining it, we're going to look up properties in tables for the identified region. For instance, if we find out that our material has the internal energy at a given pressure, its internal energy is more than the internal energy of saturated vapor, it means that we have a superheated steam. That's the reason why its energy is so high. It is steam, right? So then that now that I know I have steam, I go and find the superheated steam tables and I look up for the rest of the properties of material in those tables. Okay? If I have superheated vapor, I'll look at superheated vapor table. If I have saturated liquid vapor, which means that I'm in between two saturation condition, then I will use saturated table. And for that, I need to do some calculations. If I have compressed liquid, then I'm gonna use either the saturated liquid tables, right? If I have those tables. And this is something that happens rare because for many materials, we don't have tables for subcooled liquid, right? For compressed liquid, we usually don't have tables except for water. I think except for water, we don't have tables for most of the materials. If that is the case, instead of using the tables, we use the saturated liquid properties at the same table. All right, let me save it for now, and we are gonna keep going in the next video. Let me see. Here we go. Is this here?